Hello YouTube! Today we're going to be talking about rolling without slipping. This is kind of taking the energy stuff and being like, alright, we're finally doing the energy stuff for real. Yeah, I'm just going to dive in without saying too much more about it. Normally I kind of stall out a little bit to see if I can get an easy thumbnail shot. But ideally, end of the day, you should be able to model the motion of objects that are rolling without slipping. The big thing here is if you can relate the angular and rotational motion, you can then use that to figure out how the object is going to be spinning and how the object's going to be moving. And then set up and solve equations using that. So if a wheel is rolling without slipping, the distance traveled by the wheel will be equal to the linear distance that's traveled by the edge of the wheel. And this is sort of happening for a fairly basic reason of it's rolling, so it's rotating, and it's not slipping. So whatever points of the wheel are in contact with the floor have to trace out a sort of one-to-one mapping of the distance with the length of the floor that they travel over. This has some weird effects. The first really big one is that in order for that to happen, the bottom of the wheel needs to not be moving relative to the floor. But that means that the average velocity of the wheel as a whole needs to be such that the wheel will be moving at the speed of the wheel linearly. So the bottom of the wheel is going to be stopped or not moving. The center of the wheel, specifically the pivot center of the wheel, the axle, is going to be moving at the translational velocity of the wheel. And the top part of the wheel is going to be moving with a tangential velocity that is double the bottom of the wheel. And there are a lot of ways that you can prove that. I'd maybe recommend looking them up, but honestly, as long as you can just remember it, that should be plenty for the test. And at this point, we're probably kind of in panic mode, so we'll call it good enough. How to actually turn that into some problem solving? How long will it take for a 2 kilogram wheel of radius 0.5 meters to reach the bottom of a 10 meter tall hill with an angle of 30 degrees if there is enough friction for the wheel to roll without slipping? How will the answer qualitatively change if the wheel does not have enough friction to roll without slipping? My blue pen fell on the floor. Let me grab it. I've done it. Alright. So we have R equals 2, our angle is 30 degrees, and our height is 10 meters. And there's plenty of friction. No, our radius is not 2, radius is 0.5, our mass is 2 kilos. Alright. So A, we're trying to find the time, and B, we are checking if the friction was smaller. So there's going to be kind of a lot going on for this problem. First thing we should be doing is looking at our forces. We know that there's going to be some force of gravity going downward from the center of the wheel. We know that there's going to be some normal force going tangent to the ground and through the wheel. And we know that there's going to be some force of friction going backwards. Well, we know that our mechanical energy is actually going to stay the same because we're not losing any energy to the wheel rubbing against the ground, generating friction. So we can say that our potential energy at the beginning will need to be equal to our kinetic energy at the end plus our rotational kinetic energy at the end. Why? Oh, why? This is a weirdly a much more difficult problem than it should be. I'm going to change the problem. We're not looking for the time, we're looking for the final velocity. From there we can say that mgh is equal to 1/2 m vf squared plus 1/2 I omega squared. Well, I is going to be equal to whatever our wheel's sort of factor is. If it's a disk, it'll be 1/2 mr squared. If it's a hoop, it'll be 1 mr squared times r omega squared. But because we're rolling without slipping, r omega times r will equal our velocity for the end. So if we take this relationship and pop that in here, we get mgh equals 1/2 m vf squared plus 1/2 times 1/2 mr squared times vf squared over r squared, distributing r squared out from the terms that we plugged in. Our radius is going to drop, our mass is going to drop, and what we're left with is two terms here. Something that I'd like to highlight here is that the ratio between the amount of our energy that will be linear and the amount of our energy that will be rotational is actually going to be just the ratio of this shape factor, because we've got 1/2 mv squared, 1/2 mv squared, and the only difference here once the radius drops is this number which came from our shape. So we can use that to relate to our setup if it weren't spinning, and we can think about a decent chunk of problems that way, just sort of as at least a conceptual approach. From there we are almost done. We just have to combine like terms and divide. So we've got mg 1/2 a half plus a quarter, so 3/4 vf squared. Multiply each side by 4/3, multiply each side by 4/3. We'll get 4/3 gh equals vf squared, square root both sides, and we'll get square root of 4/3 gh is our final velocity. Now conceptually we're asked what happens if this thing starts to slip. Well, if we think about it from a forces perspective, if this thing starts to slip, instead of rolling without slipping, we're not going to be quite sure. But if this thing starts to slip instead of rolling without slipping, what we can say is that we didn't have enough force to get the thing to spin instead of moving sideways. And so because we didn't have as much force to get the thing to spin from moving sideways, we're gonna wind up losing energy as we go. And so it's a little weird if we're at a low enough angle so that the friction that would have been required to get it to spin is small enough. We're going to get into a problem where we've got two competing ideas. Our first idea is that there's energy that's actually being dissipated now because we're losing energy as heat. This means that our mechanical energy is going to wind up being lower for the whole thing. Our second competing idea here is that in addition to having less mechanical energy, we're going to be having less, potentially we could be having less force going backwards in general, because kinetic friction is actually smaller than static friction. So the weird thing here is that if we have less kinetic friction than we do static friction, from just a straight up forces perspective, the object will reach the bottom in less time and the object will reach the bottom going faster because its acceleration will be larger because the backwards force is smaller. If we have a situation where the object is was not having that much force and the kinetic friction is actually bigger than the static friction that would be required to get it to spin, and like let's say it just started out slipping and that's why it's slipping, then we're going to be in a different situation because now we wind up with more friction than we would have otherwise had, and if we get more friction than we would have otherwise had, it'll wind up reaching the bottom going slower. Yeah. I guess things to highlight here are that you are basically just taking your omega, relating that to V, and that makes it pretty straightforward to do these problems with energy. Yeah. And that ratio of the two velocities, you can also use that to, not ratio of the two velocities, ratio of the two energies. You could theoretically also potentially use that for other aspects of problem solving. All right. Next problem. Two rolls of toilet paper are dropped at the same time from different heights. One roll of toilet paper is dropped from height h and held at the end of the toilet paper as it falls. The other one is dropped from height lowercase h and is in free fall. What is the ratio of lowercase h divided by uppercase h in terms of the inner and outer diameter of the toilet paper rolls? So this is a fun one that you could theoretically do at home. Try it, figure it out, and then test your results. So actually doing it. Well, basically, for our just dropped roll where we're not doing anything special, getting our time is fairly straightforward. We know that it's going to have a fixed acceleration of gravity. We know that it's going to have an initial velocity of 0, and we know that it's going to have a height of lowercase h. So if we use the equation with those things and time, we'll get that our displacement of h is equal to 1/2 a t squared plus v naught times t. This term is 0, so I don't have to care about it. H will be equal to 1/2 g t squared, multiply each side by 2 over g, multiply each side by 2 over g, and we'll get that our time is 2hg square rooted, and that's our time to reach bottom. For our second object, assuming, and if the toilet paper is thin enough, this is a good assumption. If the toilet paper is not thin enough, this stops being a good assumption, because the diameter will be changing with time. But if we assume a sufficiently thin roll of toilet paper, what we can do is say that our equation for our second roll of toilet paper is going to be very similar, except instead of g, we'll keep our acceleration. So 1/2 acceleration times squared, still plus 0, multiply by 2, divide by the acceleration, multiply by 2, divide by the acceleration, and we'll wind up getting that root 2h over a equal to our time second toilet paper. Because these two are going to be falling for the same amount of time, they land at the same time, that'll get us that root 2h over a is equal to root 2 lowercase h over g. If we square both sides and divide by 2 and multiply and divide each side by uppercase h and multiply the side by g, we'll have something that's starting to approximate our answer. Gravity divided by the acceleration of the big one will give us the small one, the height of the small one, divided by the height of the big one. So their acceleration ratios need to be the same as their height ratios, which makes some level of sense. If that's the case, we'll now need to find our acceleration for the toilet paper tube. This is the trickier part. So the toilet paper tube that's held from a strand is going to have two things that are true. It's going to be accelerating linearly, it's going to be accelerating angularly, and it's going to have some rotational kinetic energy, although that one might be a sort of false path. If we look at the torque that's on this object, the net torque on it will need to equal I times alpha. The net torque on it is going to be the larger radius, smaller radius, and diameter would be easier to measure, but I'm just going to use radius. The force is being applied to the larger radius. So the force of our toilet paper times our larger radius will be our torque from our toilet paper. Our moment of inertia, if you look it up in a table, is going to wind up being 1/2 the big diameter squared minus the small diameter squared times times our mass. And that's going to need to equal alpha. But because this thing's rolling without slipping, our radial acceleration will need to equal, times our radius will need to equal our tangential acceleration for this object. So that will come in handy later. Let's set up our linear side of the equation, because we've kind of hit a dead end. Yes, we can get this in terms of tangential acceleration, but we don't know the force from the toilet paper. Well, if we look at our linear side of things, our net force will need to equal our mass times our acceleration, which will also be our tangential acceleration in this case. If we set it up like that, then we've got our if we set it up like that, then our net force is going to be gravity pulling us forward, and this should actually be negative because this is slowing us down, or making us rotate in a negative direction, because F down to the page. Mg minus R force from our toilet paper will need to equal mass times our tangential acceleration. So at this point, if we make this substitution here, we'll get two different equations. Tangential force will equal times our big radius equal half mass times our radius squared minus r, these should both be r, minus our smaller radius squared times our big radius, our tangential acceleration, divided by our big radius. If we multiply each side, we can take this equation divided by our big radius, and plug that in over here. When we do that, what we'll get is mg minus 1/2 m r squared minus r squared times our tangential acceleration divided by r squared equals m a t. Finally, our masses can drop, so I can stop writing that. And if we multiply each side by r squared, for the sake of making it a little easier to combine like terms later down the line, what I've now got is r squared g minus 1/2 r squared minus lowercase r squared. My tangential acceleration equals my tangential acceleration times capital R squared. If we get all our terms with a to one side, by adding that to both sides, we'll get r squared g equals 1/2 r squared minus r positive squared a t plus r squared a t. When we combine those things, we'll get r squared g equals 3/2 r squared minus 1/2 lowercase r squared, distributing that 1/2 across these two and combining like terms, at. If we divide each side by 3/2 r squared minus 1/2 r squared, 3 r squared minus 1/2 r squared, what we'll get is that our tangential acceleration will need to be equal to r squared g over 3/2 r squared minus 1/2 r squared. And if we take that and plug that in up here, what we'll find is that g divided by at equals g divided by r squared g over 3/2, and this is all in parentheses, r squared minus 1/2 lowercase r squared. Flipping our fraction in the denominator, g's are going to drop. and we'll get 3 halves r squared minus 1/2 lowercase r squared divided by the radius squared will be our height ratio we were looking for. So our key things we did here were lots of algebra, but by setting the two times equal to each other, we could compare their acceleration ratios as compared to their height ratios. Now that we knew that the problem could potentially be related to acceleration, we set up a linear acceleration problem, but that included a force we didn't know. So we set up an angular acceleration problem and used the relationship between the angular and the linear to tie those two equations together. And tying those two equations together, we were able to throw them back up here and get our final answer. So that's pretty much it. Goodbye, YouTube.